This will be a problem session for section 6. Chapter 6 in the book. Let me start with section 6.1. In the problems I have assigned for this section, most of them are straightforward. One just applies the definition of ideal and in a straightforward way shows whatever the book asks to show. So if I overlooked nothing, most of these problems should be easy. I found one tricky problem which I want to comment on, and this is 22 on page 149. There are other tricky problems I tried to avoid because, in my opinion, they are a little bit besides the point for this class. So in this problem, we have I and J ideals in a ring R. And they define a subset of R as the subset of products AB, where A comes from I and B comes from J. They ask whether K is again an ideal. There is an exercise when it is A plus B, and it is easy to prove that it is an ideal. However, in this case, this may be not an ideal. And a counterexample is not so easy to come up with, so I will show you. So, example, when K is not an ideal, will be the following. For the ring R, we will take the ring of polynomials with integral coefficients. We will take I and J to be the same, namely the ideal generated by two elements of the ring R, 2 and x. This is a finitely generated ideal, though, as we once already discussed, not a principal ideal. As a set, this is the set of all polynomials with integral coefficients with even constant term. Now, it is clear that K contains 4 because I contains 2, J contains 2, we take their product, it is 4. So element 4 is there, and by a similar token, K contains x squared because I contains x, J contains x, so we take x for A, x for B, x squared must be in K. However, K does not contain their sum. What I want to say that this polynomial 4 plus x squared, of course, 4 plus x squared is an element of the ring R, 0 of x. This polynomial cannot be presented as a product of two polynomials with even constant terms. That may be justified. So what I want to say that 4 plus x squared is not a product of two polynomials with integral coefficients and even constant terms. Even constant terms does not really matter it matters, in fact, because the only way to present it as a product of two polynomials, one of these two polynomials is going to be 1 and negative 1. 1 and negative 1 simply does not have constant, even constant term. The constant term is either 1 or negative 1, which is odd. Indeed, a point is that this polynomial is a polynomial in z of x, and actually every polynomial in z of x is a polynomial with rational coefficients. It is much easier to work in this bigger ring because these polynomials have their coefficients in a field, and we know a lot about this case. So if the polynomial factors into two polynomials, these of positive degrees, these positive degrees should be 1, and the polynomial should be reducible. So first of all, 4 plus x squared as a polynomial in Q of x is irreducible therefore does not factor into a product of two polynomials of positive degree in principle. An irreducible polynomial may factor, but this one has degree 2. So if it factors, it must have a root. It does not have a root, therefore is irreducible. So it does not factor into two polynomials of positive degree. It does not factor in Q of x, therefore it does not factor in z of x, because every polynomial with integral coefficients is a polynomial with rational coefficients. So it is irreducible, it does not factor. So the only possible presentation of the only possible presentation for plus x squared to be a times b happens when either a or b is an integer. We want to factor this polynomial into an elements of I and j, which are both elements of our polynomial ring. So now this cannot be two polynomials of positive degree, so one of these factors must be an integer. Now to get, so this is an integer times a polynomial. Now we'll look at the leading term and understand that the integer must be so looking at the leading term of x squared, we conclude that the integer must be plus or minus 1, which is not an element of I and j. So there is no factorization. No, that is more or less obvious. You write just an integer times a quadratic polynomial. Look what may be the leading coefficient of quadratic polynomial, and this integer, the leading coefficient, their product must be 1, so both are plus or minus 1, but plus or minus 1 is not in the ideal. And that's pretty clear because plus or minus 1, or plus 1 is the identity in this ring. So if plus or minus 1 is there, then the ideal IOJ is the whole ring immediately. It is not. These are only polynomials with even constant term. It is not the whole ring Z of X, so the polynomial does not factor. Here is a remark about why this example is not trivial. The first rings which we considered were the ring of integers or the ring of polynomials. So in the rings Z or polynomials with coefficients in a field, in both these rings, every ideal is principal. It is not difficult to prove that using Euclid's lemma, also known as division algorithm in the book. As soon as, and therefore, in these rings, such an example is not available. Well, show you that as a proposition, a very simple one. F R, the ring R, is commutative I and J are principal ideals generated by some elements A and B, let us write this way, and so if the ring is commutative and the ideals are principal, then our K, which is AB, or let me rewrite it, the principal ideals, let us put them as I to be X and J to be Y. Some X and Y, some elements of the ring, and our K, which is AB for A, all A in I, all B in J, is an ideal. So you cannot, for this reason, you cannot find any examples in these rings. In these rings, every ideal is principal, so you multiply ideals and produce again an ideal. Here is a very simple proof why this is the case. You write any element A in. What does it mean? Let me recall what does it mean. The ideal is principal. This means that I, as a set, is x times r for all r in the ring R. That is the definition of what a principal ideal is. And J, of course, is similarly generated by Y, another principal ideal, Y R, all R in R. I will write R1 here and R2 here to immediately show you what the set K looks like in this case. So K is defined A, B, but any A is X R1, any B is Y R2, R1 and R2 are two arbitrary elements of R, which is xy times product of two arbitrary elements of R. I used the fact that I assumed the ring was commutative. And the set of all products of elements of R, or commutative ring, for simplicity, let it be with identity. So that we see that the set of all products of all elements of R is the whole ring, because you can take one of them identity, another one any element of the ring, so any element of the ring appears here maybe several times. Does not matter. So this is same thing as xy are any element of the ring R. And now what we got is, by definition, the principal ideal generated by xy. So in these cases, you will not find an example such that K is not an ideal. It is, again, simply the principal ideal generated by the product of x and y, as this simple calculation shows. So, therefore, starting from this observation, for the example here, we needed an ideal which is not principal. We once proved that this ideal is really not principal. There is no element in this polynomial ring to generate this whole ideal. We once proved this statement. Anyway, because somehow the knowledge, not the proof, but just the knowledge that this ideal, not only written as a non-principal ideal, but indeed as a non-principal, gives a hope that that is going to be a counterexample. And indeed, as you see, the set K not only is not an ideal, it is not a subring. In fact, because it has two elements, but not their sum. So let me write it. K is not even a subring of R. So we show that the sum is not in K. This polynomial cannot be written as a product of two elements, one from I, one from J, meaning from the same product of two elements of this ideal. In fact, the polynomial is irreducible and can be written only as 1 times the polynomial. Or, by the way, instead of the consideration of leading coefficient here, you may say that because polynomial is irreducible, in Q, all factorizations in Q are unit in Q of x. It is unit times an associate. But units here, there are many units here, but there should be a factorization valid here. So here the units are only plus or minus 1. That kind of argument instead of the consideration of leading term, which I suggested, is also possible in this exercise. In the next fragment, I will jump to section 6.2 from the book and show you a couple of exercises from that section. Thank you for listening.